Welcome, ladies and gentlemen. My name is Anja Heim and I'm working at the University of Applied Sciences, Upper Austria. And today I want to talk about our framework CoSi, which enables a visual comparison of similarities in high-dimensional data ensembles. So CoSi was initially developed to support the exploration of materials. And to be useful in our daily activities, materials have to fulfill certain properties. For example, the material of this wind turbine has to be resistant and durable. And these properties are induced by the inner structure of the materials. Specimens can consist of fibers and pores, and the distribution of these features and their characteristics, like the length or the diameter, can determine the properties of the specimen. Through X-ray computed tomography, we can produce images of the internal structures of the materials. And through segmentation and quantification algorithms, we can then identify the features and their characteristics. And now material engineers want to analyze these tabular high-dimensional datasets. And to get concrete insights about the properties of the materials, experts that now do not only want to examine one specimen, but several. And further, they also want to perform in situ tests. And there, a force is applied to a specimen for a certain time, and then an XCT scan is performed. And this procedure is then repeated a certain number of times, and experts then want to compare these time-varying datasets. So our analysis goals are on the one hand to compare various specimens, then to compare a specimen over time, and finally also the combination of both should be possible, so to compare various specimens over various time steps. And to fulfill our analysis goals, our contribution is a design study of our visual analysis framework CoSi, that enables a comparison of hundreds to thousands of features from dozens of datasets. And to show its effectiveness, we demonstrate 2 use cases, and we performed a qualitative user study with 12 material experts. To achieve our analysis goals, we abstracted 3 different tasks during intensive discussions with our experts. So first it became clear that we would need a visualization to make a comparison of the similarity among the individual ensemble members possible. In an overview visualization, therefore, it should be possible to identify similar groups of features. Secondly, we would need a visualization in which a comparison among the ensemble members' characteristics would be possible. So here it was important that the details which would be lost in the overview visualization could be made available again. And lastly, the experts needed some additional information in which they could make assumptions about the pairwise correlations of the characteristics. And to accomplish these 3 different tasks, we developed 3 different visualizations. The ensemble Similarity Explorer to show an overview, the Similarity Widget to get more detailed information, and the Correlation Widget to get information about the correlations. So, and here we can see the structure of CoSi. On the top we can see the Similarity Widget, the Ensemble Similarity Explorer, then here is the Similarity Widget, and here we can see the correlation coefficient map. And so first we go to the Ensemble Similarity Explorer, and it is constructed like this. Each row represents an ensemble member, and each ensemble member consists of rows of features with their characteristics. And we apply multidimensional scaling to aggregate each feature to a similarity value. And then each feature is positioned according to this similarity value on this horizontal line. So, and this is done for all datasets. And so for all features of these datasets are then positioned on this horizontal line. All features of the second ensemble member are then positioned on the second horizontal line, and so on. And based on the similarity values, now the features that lie in close proximity are similar, while features that are positioned further apart are dissimilar. And since all the features of all datasets are taken into account for the same computation, also the features lying vertically beneath each other are similar. So now the problem with this point representation is that when we have a lot of features, then this representation gets cluttered quite fast. And therefore we applied a binning and divided each line into 10 individual bins. And we colored these bins according to the number of features located in them. So now it is possible to identify similar datasets according to their color patterns. For example, here we can see in situ test of a fiber specimen. There a force was applied to it for 10 minutes, and then the force was applied again for 60 minutes. And for more detailed investigation, the specimen was divided into 4 equally sized regions. And here in our overview visualization, we can see that the regions have very similar fibers. Here, for example, in region 1 of 10 minutes and 60 minutes. But we can also see that the force affected the fibers. For example, here in region 4, we got it is after 10 minutes, and the fibers are shifted a bit to the left after 60 minutes. So the only problem now of this visualization is we can see where similar groups of fibers are located, but we cannot see why they are similar, or more precisely in which characteristics they are similar. So, and therefore we added the Similarity Widget. In the Similarity Widget, we can see a bar chart and a box plot. The bar chart tells us in which characteristics the features are most similar in, and the similarity score is computed with the coefficient of variation. So here we can, for example, see that the characteristic curved fiber is the most similar one for all features. And then the box plot shows us two different things. On the one hand, the distribution of the characteristics. So when the box is very small, then we can say that the variation is very small, so therefore this characteristic is quite similar. And on the other hand, according to the positioning of the box, we can see if the characteristics had smaller or higher values. Here, for example, the characteristic volume. Here the box is positioned quite low, so therefore the fibers in this example have a quite small volume. So, and lastly, CoSi provides the correlation widget. Here we can see the correlations computed according to the Pearson correlation, and each vertex here represents a characteristic, and the edges between them encode the correlation information. So a positive correlation is drawn in red, a white correlation, when there's no correlation, it is drawn in white, so it is invisible for the user, and a negative correlation is drawn in blue. And the circular segments around the graph show the relation of the numbers of the features for each dataset. So in this example, the datasets segment have quite the same size and have therefore about the same number of features. So, and now we can see a demonstration of the interactivity of our framework. First, we will see the linear binning, where the bin size is reduced to get a more precise image of the distribution. Then a ranking is performed according to the whole data set. Then a ranking according to one individual bin is performed, and a ranking through different bins is performed. And now we will see the nonlinear zooming function. Here we can scroll down to the point representation. And now we'll see the nonlinear zoom a second time, and here we can look at the interactivity of the different charts. So the selected features are then overlaid over the original ones. So for our evaluation, we performed two use cases, one showing an in situ test of a fiber specimen, which I've showed you before, and the other use case was a comparison of two pore specimens. Here a small specimen was compared with one bigger specimen, which was then divided into 5 adjacent regions. And further, we performed a qualitative user study with 12 material experts. During this study, they had to solve 7 predefined tasks to test the comprehensibility and the applicability of CoSi. To shortly reflect on our method, we had very regular discussions on the visualizations with the material experts, and especially about the aggregation to 1D. This was intensively discussed, but in the end it was seen as appropriate since CoSi for CoSi the focus was on the development of an overview visualization. And the most surprising finding was that in the evaluation, the experts also like to explore a single dataset beforehand in more detail, and then they compared it against others. So CoSi is a highly scalable framework. The number of features or characteristics is merely limited by the run, since we use the Markov algorithm to compute the multidimensional scaling. And further, with CoSi, the number of members to be compared is quite high, so approximately 50 members shouldn't be a problem, since mainly the color patterns are crucial for identifying similar datasets. And lastly, although CoSi was developed with the intent to support material experts in their daily workflow, CoSi can be used for any high-dimensional multivariate dataset, independent of any discipline, since we do not use any domain-related information for the computations. And this image here shows a general information visualization dataset where we compared the unemployment rate of various countries for men and women of 3 different age groups. So, and with this, I want to thank you for your attention.